The Great Pyramid of Giza stands before you like a mountain built by human hands, rising from the desert sands with an authority that has commanded respect for over 4,500 years. When you crane your neck to take in its full height, something profound happens. Your mind starts racing, trying to process the impossible mathematics of what you're seeing. 2.5 million limestone blocks, each one weighing as much as a small car, stacked with precision that would challenge modern engineers. And then the questions begin flooding in. How did they move stones weighing 15 tons without cranes? How did they achieve accuracy measured in millimeters across a base spanning 13 acres? How did farmers and craftsmen working with copper tools create something so perfect that it held the record as the world's tallest structure for nearly 4,000 years? For too long, we've been offered two unsatisfying answers to these questions. The first suggests that ancient Egyptians were somehow primitive people who got lucky with some basic techniques. The second throws up its hands entirely and claims that extraterrestrial visitors must have intervened because humans couldn't possibly have managed such feats. Both explanations are wrong, dead wrong. The truth is far more fascinating than either alternative. The ancient Egyptians weren't primitive at all. They were sophisticated engineers, brilliant mathematicians, and organizational masters who developed revolutionary techniques that we're only now beginning to fully understand. They didn't need aliens because they had something even more powerful: human ingenuity operating at its absolute peak. Tonight, we're going to walk through exactly how these monuments were actually built, step by step, block by block. We'll explore the ingenious solutions that ancient engineers developed to overcome seemingly impossible challenges. We'll examine the evidence that archaeologists have uncovered through decades of painstaking research. And we'll discover why the real story of pyramid construction is more impressive than any alien conspiracy theory could ever be. But before we dive into ramps and levers and copper chisels, we need to understand something crucial. The pyramids weren't built by slaves dragging blocks across the sand while being whipped by cruel overseers. That Hollywood image is completely false. Recent archaeological discoveries have revolutionized our understanding of who actually built these structures and how they lived while doing it. The workers who constructed the Great Pyramid were skilled Egyptian laborers who took enormous pride in their work. They weren't slaves at all. They were paid employees who received daily rations of bread and beer, lived in well-organized worker villages, and even had access to medical care when they were injured on the job. Archaeological excavations near the pyramids have uncovered these worker settlements, complete with bakeries that could produce enough bread to feed thousands of people daily. These weren't just any workers either. The core workforce consisted of highly trained craftsmen who worked year-round on pyramid construction. During the annual flooding of the Nile River, when farming became impossible, this permanent crew was joined by thousands of seasonal workers from across Egypt. Picture it. Every year, as the Nile waters rose and covered the farmland, skilled farmers would make their way to Giza to contribute their labor to these monumental projects. The scale of organization required was staggering. Estimates suggest that anywhere from 20,000 to 30,000 people worked on the Great Pyramid at any given time. These workers were divided into specialized teams, each with specific responsibilities. Some quarried limestone blocks from nearby sites. Others transported these massive stones to the construction area. Master stonemasons shaped and fitted the blocks with incredible precision. Engineers and architects oversaw the entire operation, ensuring that every element aligned perfectly with their grand design. Managing this workforce required administrative skills that rival modern corporations. The ancient Egyptians developed sophisticated systems for tracking materials, coordinating labor schedules, and maintaining supply chains that stretched across the entire kingdom. They created detailed records of worker assignments, food distributions, and construction progress. Some of these administrative documents have survived, giving us glimpses into the remarkable bureaucratic machine that made pyramid construction possible. Now let's talk about the stones themselves, because this is where the engineering challenges become truly mind-boggling. The Great Pyramid contains approximately 2.5 million individual blocks. The average block weighs about 2.5 tons, but some of the granite blocks used in the internal chambers weigh up to 70 tons. To put that in perspective, 70 tons is equivalent to about 50 modern automobiles stacked together. These blocks didn't magically appear at the construction site. They had to be quarried from limestone deposits located nearby, and in the case of granite blocks, from quarries at Aswan, over 500 miles south of Giza. The limestone quarrying process was itself an engineering marvel. Workers used copper chisels and bronze saws to cut precise channels around the blocks they wanted to extract. They employed wooden wedges that would be soaked with water, causing the wood to expand and split the stone along predetermined lines. But quarrying was just the beginning. Once these massive blocks were freed from their bedrock, they had to be transported to the pyramid site. For the limestone blocks quarried nearby, this involved moving stones across relatively short distances, but often over uneven terrain. For the granite blocks from Aswan, it meant loading them onto specially constructed boats and floating them down the Nile River during the annual flood season when water levels were high enough to support such heavy cargo. The transportation challenge becomes even more impressive when you consider the precision required. These weren't just rough stone blocks that could be shaped later. Many of them were pre-cut to exact specifications at the quarry sites. This means that workers had to transport blocks that were already precisely shaped to fit into specific positions within the pyramid structure. There was no room for error. Once the blocks reached the construction site, the real engineering magic began. The ancient Egyptians had to develop methods for lifting stones weighing several tons to heights that eventually reached nearly 500 feet above ground level. They had no pulleys, no wheels for transportation, and no steel cables. What they did have was an understanding of physics principles that allowed them to multiply human force through clever mechanical advantage. The foundation work alone demonstrates the sophistication of their approach. Before the first block could be placed, the entire base of the pyramid had to be leveled with extraordinary precision. The Great Pyramid's base is almost perfectly flat, with variations of less than an inch across its entire surface. To achieve this level of accuracy, the builders created a network of water-filled channels across the construction site. Water always seeks its own level, so by marking the water level at different points and then removing excess rock to match those marks, they could create a surface that was flat to within millimeters. This leveling process required advanced surveying techniques that we're only now beginning to fully appreciate. The ancient Egyptians developed tools and methods that allowed them to measure angles, establish straight lines over long distances, and maintain consistent elevations across the entire construction area. They used plumb bobs, which are weights suspended on strings that always point directly downward due to gravity. They employed sophisticated leveling instruments that could detect minute variations in height. They created measuring rods and surveying equipment that enabled them to maintain accuracy across distances spanning hundreds of feet. The mathematical precision embedded in the pyramid's design reveals another layer of sophistication that challenges any notion of primitive construction methods. The Great Pyramid's base forms an almost perfect square, with sides that differ in length by less than 2 inches across distances of over 750 feet. The pyramid's faces are aligned to the cardinal directions with an accuracy that deviates from true north by less than 1/10 of 1 degree. This level of precision requires not just advanced surveying techniques, but also deep knowledge of astronomy and celestial navigation. The builders used their understanding of star positions to establish true north with remarkable accuracy. They likely observed the rotation of circumpolar stars, which appear to circle around the north celestial pole, and used these observations to determine precise directional alignments. This astronomical knowledge was then translated into practical construction techniques that ensured the entire pyramid would be oriented correctly. Perhaps most impressively, the pyramid's proportions incorporate mathematical relationships that wouldn't be formally described by mathematicians until centuries later. The ratio of the pyramid's height to the perimeter of its base closely approximates the mathematical constant pi. Whether this was intentional or resulted from their construction methods, it demonstrates a level of mathematical sophistication that contradicts any suggestion of primitive building techniques. The internal structure of the pyramid reveals even more engineering brilliance. The Great Pyramid contains multiple chambers connected by precisely aligned passages. The Grand Gallery, a corridor that rises at an angle through the heart of the pyramid, showcases masonry work that rivals anything produced in the modern era. The blocks that form this gallery are fitted together so precisely that you cannot slide a knife blade between them. The King's Chamber, located deep within the pyramid, was constructed entirely from granite blocks that had to be transported from Aswan and then somehow maneuvered into position within the growing structure. This chamber demonstrates not only the builder's ability to work with extremely hard stone, but also their understanding of structural engineering principles. The chamber is topped by a series of relieving chambers designed to distribute the enormous weight of the pyramid above it, preventing the collapse of the burial chamber below. These relieving chambers represent one of the most sophisticated applications of structural engineering found in the ancient world. The builders understood that simply stacking millions of tons of stone would create crushing forces that could destroy any chambers within the structure. So they designed a system of voids and supporting elements that channeled these forces around the critical spaces, allowing the chambers to remain intact despite the incredible loads pressing down from above. The precision of the stonework throughout the pyramid suggests manufacturing processes that we're only beginning to understand. The surfaces of many blocks are so smooth and flat that they appear to have been machine finished. The joints between blocks are so tight that mortar wasn't even necessary in many cases. The weight of the stones themselves, combined with their precise fit, created structural integrity that has lasted for millennia. This level of precision wasn't achieved through luck or primitive techniques. It required sophisticated tools, advanced measuring instruments, and manufacturing processes that demonstrate a deep understanding of materials, science, and engineering principles. The ancient Egyptians developed copper alloys that were harder than pure copper, allowing them to cut and shape stone with remarkable accuracy. They created abrasives and cutting compounds that enhanced the effectiveness of their tools. They understood the properties of different types of stone and selected materials based on their specific characteristics and intended uses. The organizational systems required to coordinate this level of precision across such a massive project rival anything found in modern construction. Every block had to be quarried to specific dimensions, transported without damage, and positioned exactly where it belonged within the overall structure. This required communication systems, quality control processes, and project management techniques that demonstrate administrative capabilities far beyond what we typically associate with ancient civilizations. As we delve deeper into the actual construction methods in the next part, you'll discover that every aspect of pyramid building required innovations that pushed the boundaries of what was possible with the technology available at the time. The ancient Egyptians weren't primitive people stumbling toward accidental greatness. They were sophisticated engineers who developed revolutionary solutions to engineering challenges that would intimidate even modern construction teams. The story of how the pyramids were actually built is a testament to human ingenuity, determination, and the power of organized effort. No aliens were required because human beings, when working at their intellectual and organizational peak, are capable of achievements that seem impossible to later generations who have forgotten the techniques and lost the institutional knowledge that made such feats possible. The mystery of how massive stone blocks were actually moved and positioned has puzzled observers for centuries, but the evidence points to solutions that are both elegant and surprisingly practical. The ancient Egyptians didn't defy the laws of physics. They mastered them. Let's start with the most fundamental challenge. Moving blocks that weigh as much as military tanks using nothing but human power and simple machines. The key breakthrough came when archaeologists realized that the Egyptians had discovered something that modern physics confirms. Friction, the force that resists movement between surfaces, can be dramatically reduced with the right techniques. Recent experiments have demonstrated that wet sand creates an almost magical reduction in the effort required to pull heavy sleds. When workers poured water in front of wooden sleds carrying multi-ton blocks, they could reduce the pulling force needed by up to 50%. Picture this. Instead of requiring 100 men to drag a massive stone, the same block could be moved by 50 workers once the sand was properly dampened. This wasn't just theoretical knowledge. Archaeological evidence shows that ancient Egyptian artwork frequently depicts workers pouring water in front of sleds, carrying large statues and building materials. What previous generations of researchers dismissed as ceremonial or symbolic behavior was actually sophisticated engineering technique being recorded for posterity. The sleds themselves were marvels of practical engineering. Constructed from sturdy hardwood beams, these devices distributed the weight of massive blocks across a broader surface area, preventing them from sinking into soft ground. The runners of these sleds were often reinforced with bronze strips or treated with animal fat to further reduce friction. Some sleds were designed with curved runners that rocked slightly as they moved, helping to break the static friction that makes it hardest to get heavy objects moving in the first place. But sleds were just one part of the transportation system. The Egyptians also mastered the use of wooden rollers, cylindrical logs that could be placed beneath heavy loads to transform dragging motion into rolling motion. Teams of workers would continuously reposition these rollers, moving them from behind the load to the front as the stone advanced. This technique reduced friction even further and allowed relatively small teams to move enormous blocks across considerable distances. The coordination required for this roller system reveals another layer of organizational sophistication. Workers had to move in perfect synchronization, with some teams pulling the load while others managed the rollers. A single mistake could result in crushed limbs or damaged blocks. The fact that this system worked consistently across years of construction demonstrates training and teamwork that rivals modern industrial operations. For the heaviest blocks, weighing 40 tons or more, the Egyptians developed even more ingenious solutions. They created specialized heavy-duty sleds with multiple runners and reinforced construction. They organized larger work gangs, sometimes involving hundreds of men pulling in coordinated efforts. Most importantly, they planned transportation routes that minimized the challenges these massive blocks would encounter. The route planning itself was a masterpiece of logistics. The Egyptians built dedicated roads between quarry sites and construction areas, carefully graded to avoid steep inclines and engineered to handle the extreme loads that would travel along them. These weren't simple dirt paths. They were constructed roadways with prepared surfaces, drainage systems, and even rest stations where work crews could pause during long hauls. When the annual Nile flood arrived, the transportation system shifted to take advantage of the river's power. The Egyptians constructed specialized barges capable of carrying the heaviest granite blocks from distant quarries. These weren't ordinary boats. They were engineering projects in their own right. Massive wooden platforms designed to remain stable while loaded with stones weighing dozens of tons. The engineering challenges of river transport were formidable. A barge carrying a 70-ton granite block had to maintain stability while navigating a river that could become turbulent during flood season. The ancient shipbuilders developed hull designs that distributed weight evenly and created vessels with enough buoyancy to handle extreme loads. They used multiple steering oars and sophisticated anchor systems to maintain control during the journey downstream. Loading and unloading these massive blocks from barges required yet another set of specialized techniques. The Egyptians built temporary harbors and loading facilities that could handle the extreme weights involved. They developed systems of ramps and levers that allowed blocks to be transferred from barges to land-based sleds without damage. Some evidence suggests they even created floating dry docks that could be partially submerged to ease the loading process. Once blocks reached the pyramid construction site, the real engineering magic began. This is where the Egyptians had to solve a problem that would challenge modern construction teams. How do you lift multi-ton blocks to heights approaching 500 feet using only human power and simple machines? The answer lies in one of humanity's oldest and most powerful mechanical inventions, the ramp. But these weren't simple inclined planes. The Egyptians developed sophisticated ramp systems that evolved as the pyramid grew taller, creating a dynamic construction platform that adapted to changing requirements throughout the building process. The most widely accepted theory suggests that the Egyptians used a combination of straight ramps for the initial construction phases and spiral ramps that wrapped around the pyramid as it grew taller. The straight ramps provided a direct route for moving blocks during the early stages, when the pyramid was still relatively low. These ramps were substantial structures in their own right, built from limestone chips, mud bricks, and wooden reinforcements. As the pyramid grew higher, the straight ramp system became impractical. The ramps would have had to extend enormous distances to maintain a manageable slope, eventually requiring more material than the pyramid itself. This is where the spiral ramp system came into play. Recent computer modeling and archaeological evidence suggests that the Egyptians built ramps that curved around the growing pyramid, creating a continuous pathway to the top that maintained a workable grade throughout construction. These spiral ramps were engineering marvels that required constant modification as construction progressed. Workers had to continually extend and reshape the ramps to accommodate the pyramid's changing geometry. The ramps themselves had to be strong enough to support not just the weight of the blocks being transported, but also the teams of workers, sleds, and equipment moving along them. The construction of these ramps reveals another dimension of Egyptian engineering sophistication. The ramps couldn't simply be piles of dirt and rocks. They needed carefully engineered surfaces that would provide stable footing for work crews while being smooth enough to allow sleds to move efficiently. They required drainage systems to prevent erosion during rainstorms. They needed reinforcement structures to prevent collapse under the extreme loads they would carry. Archaeological evidence suggests that different sections of the ramp system were specialized for different purposes. Some portions were designed for upward traffic, carrying blocks toward their final positions. Other sections handled downward traffic, allowing empty sleds and equipment to return to ground level. The most sophisticated sections included passing areas where upward and downward traffic could navigate around each other without causing dangerous bottlenecks. The precision required in ramp construction was extraordinary. The grade had to be steep enough to minimize the total length and material requirements, but gentle enough to allow heavily loaded sleds to be pulled up the incline. Modern calculations suggest that the optimal angle was probably around 7 to 8 degrees, steep enough to be efficient but manageable for teams of workers pulling heavy loads. But ramps alone couldn't solve all the lifting challenges. For the heaviest blocks and the most precise positioning work, the Egyptians developed sophisticated lever systems that multiplied human force through mechanical advantage. These weren't simple crowbars. They were precisely engineered tools designed to lift, position, and fine-tune the placement of massive stone blocks. The levers used in pyramid construction were substantial wooden beams, often reinforced with metal fittings and designed to handle enormous loads. Teams of workers would coordinate their efforts, using multiple levers simultaneously to lift blocks that weighed several tons. The fulcrum points for these levers were carefully positioned to maximize mechanical advantage while maintaining control over the lifting process. Archaeological evidence shows that the Egyptians understood the mathematical principles underlying lever mechanics. They knew that longer lever arms provided greater mechanical advantage, allowing smaller forces to move larger loads. They also understood that the positioning of the fulcrum point determined both the amount of force multiplication and the distance through which the load would move. For the most challenging lifts, the Egyptians developed compound lever systems that used multiple stages of mechanical advantage. A smaller lever might be used to position a fulcrum block, which would then serve as the pivot point for a larger lever capable of moving the actual building block. This cascading system of mechanical advantage allowed relatively small teams of workers to accomplish lifting tasks that would otherwise require enormous numbers of people. The precision positioning of blocks required even more sophisticated techniques. Once a block was lifted to approximately the correct height, it had to be moved horizontally into its exact position within the pyramid structure. This final positioning often required adjustments measured in fractions of inches across blocks weighing several tons. The Egyptians developed specialized tools for this precision work. They used wooden wedges that could be driven between blocks to create small adjustments in position. They employed bronze crowbars designed for fine-tuning the placement of heavy stones. They even created systems of rope and pulley arrangements that allowed precise control over the movement of blocks during final positioning. The mathematical precision required for this positioning work was extraordinary. Each block had to fit perfectly with its neighbors, maintaining the pyramid's geometric accuracy while supporting the tremendous loads that would be placed above it. A single misplaced block could create problems that would compound as construction continued, potentially compromising the structural integrity of the entire pyramid. Quality control during construction required systematic approaches that ensured every block met the necessary standards. The Egyptians developed measuring tools and techniques that allowed them to verify the dimensions and positioning of blocks as they were installed. They used plumb bobs to ensure vertical alignment, water levels to maintain horizontal surfaces, and measuring rods to verify distances and angles. The sophistication of these quality control systems becomes apparent when you examine the finished pyramid. The Great Pyramid's base is square to within inches across a perimeter of over 3,000 feet. Its faces rise at consistent angles that vary by less than a few minutes of arc. The internal passages maintain precise alignments that extend hundreds of feet through the structure. This level of accuracy couldn't result from casual construction methods. It required systematic measurement, verification, and correction throughout the entire building process. The tools used for this precision work were themselves masterpieces of ancient technology. Egyptian craftsmen created bronze instruments calibrated to extraordinary accuracy. They developed measuring systems based on the royal cubit, a standard unit that remained consistent across the entire project. They manufactured plumb bobs weighted with lead or stone that provided reliable vertical references even in windy conditions. Perhaps most impressively, the Egyptians understood the cumulative nature of construction errors and developed systems to prevent small mistakes from growing into major problems. They established reference points and control lines that could be used to verify the accuracy of work throughout the construction process. They created checkpoint systems that ensured each phase of construction met specifications before the next phase could begin. The coordination of all these systems, from quarrying and transportation to lifting and precision positioning, required project management skills that rival anything found in modern construction. The Egyptians had to synchronize the work of thousands of people, coordinate the delivery of materials from multiple sources, and maintain quality standards across a construction project that lasted for decades. This coordination was achieved through sophisticated administrative systems that tracked every aspect of the construction process. Written records documented the assignment of work crews, the delivery of materials, and the completion of construction milestones. Supervisors at multiple levels ensured that work proceeded according to plan and that problems were identified and corrected quickly. The scale of this administrative challenge becomes clear when you consider that the Great Pyramid required the coordination of multiple quarry operations, transportation networks spanning hundreds of miles, specialized manufacturing operations for tools and equipment, food production and distribution systems to feed thousands of workers, and construction activities that had to proceed in carefully sequenced phases. The success of this massive organizational effort demonstrates administrative capabilities that challenge our assumptions about ancient civilizations. The Egyptians didn't just possess advanced engineering knowledge. They had developed management systems capable of implementing that knowledge on a scale that wouldn't be matched again for thousands of years. As we continue exploring the construction process, we'll discover how the Egyptians solved even more complex challenges, from creating perfectly smooth interior chambers to installing massive granite blocks in locations that seem impossible to reach new layers of ingenuity and sophist. Every solution reveals occasion that make the alien hypothesis not just unnecessary, but almost insulting to the remarkable achievements of human engineering and organization. The interior chambers of the Great Pyramid present construction challenges that push ancient engineering to its absolute limits. Imagine trying to create perfectly smooth granite rooms deep inside a growing mountain of limestone blocks. Rooms so precise that their walls meet at 90-degree angles accurate to within fractions of degrees. Chambers that would remain accessible through narrow passages while millions of tons of stone accumulated above them. The King's Chamber, located in the heart of the pyramid, showcases engineering solutions that seem almost impossible given the available technology. This room is constructed entirely from red granite blocks quarried at Aswan, over 500 miles away. Each block weighs between 25 and 80 tons. These weren't just transported to Giza and then casually installed. They had to be maneuvered through narrow passages, lifted to precise heights within the growing structure, and positioned with millimeter accuracy to create walls and ceiling that remain perfectly intact after more than 4 millennia. The logistics of installing these granite blocks reveal planning capabilities that rival modern project management. The blocks couldn't be installed after the pyramid was completed because the passages leading to the king's chamber are narrower than the blocks themselves. This means the chamber had to be constructed as the pyramid grew around it, with granite blocks being positioned at exactly the right moment in the construction sequence when they could still be maneuvered into place. Consider what this required. The construction teams had to coordinate the delivery of specific granite blocks to arrive at the construction site precisely when the pyramid had reached the correct height. They had to have lifting and positioning systems ready to handle these extreme weights at considerable heights above ground level. They had to maintain perfect alignment and spacing to ensure the chamber would be geometrically correct when completed. The ceiling of the king's chamber presents even more extraordinary engineering challenges. 9 massive granite beams, each weighing approximately 50 tons, span the width of the chamber to form its roof. These beams had to be lifted to a height of nearly 300 feet above ground level and positioned with such accuracy that they create a perfectly flat ceiling with joints so tight that you cannot insert a sheet of paper between them. Above this granite ceiling lies one of the most sophisticated structural engineering solutions found in the ancient world, the relieving chambers. These 5 separate voids, stacked one above the other, were designed to prevent the crushing weight of the pyramid from destroying the king's chamber below. The engineering principles involved demonstrate understanding of load distribution and structural mechanics that wouldn't be formally described by engineers until thousands of years later. The relieving chambers work by redirecting the enormous compressive forces generated by the pyramid's mass. Instead of allowing these forces to concentrate directly above the king's chamber, the system of voids and supporting structures channels the loads around the chamber, distributing them to the solid masonry on either side. The uppermost relieving chamber features a peaked roof constructed from massive limestone blocks, arranged in a triangular configuration that further deflects the forces pressing down from above. Creating these relieving chambers required construction techniques that boggle the mind. Workers had to build hollow spaces within the solid masonry of the pyramid, spaces that would remain stable and accessible even as millions of tons of additional stone were added above them. They had to position supporting blocks with mathematical precision to ensure the load distribution would work correctly. They had to coordinate the construction of multiple chambers simultaneously, maintaining proper spacing and alignment throughout the process. The precision of the stonework in these chambers defies explanation by primitive construction methods. The granite blocks are fitted together so perfectly that the joints between them are virtually invisible. The surfaces are polished to a smoothness that approaches modern machine shop standards. The right angles where walls meet floors and ceilings are accurate to within minutes of arc across spans of 20 feet or more. This level of precision required manufacturing capabilities that we're only beginning to understand. The ancient Egyptians developed cutting and shaping techniques that could produce flat surfaces accurate to within thousandths of an inch. They created finishing methods that could polish granite to mirror-like smoothness using abrasives and techniques that remain mysterious even today. The tools required for this precision work were themselves marvels of ancient technology. Bronze saws reinforced with cutting compounds could slice through granite blocks weighing dozens of tons. Copper chisels, repeatedly annealed and resharpened, could carve intricate details in the hardest stone. Abrasive powders made from crushed quartz and other materials could polish surfaces to extraordinary smoothness. But tools alone couldn't achieve this precision. It required measurement and quality control systems that ensured every cut, every surface, and every joint met exacting standards. The Egyptians developed measuring instruments calibrated to extraordinary accuracy. They created reference standards that remained consistent across the entire project. They established quality control procedures that caught and corrected errors before they could compound into larger problems. The narrow passages that connect the chamber system to the outside world present their own engineering mysteries. The Grand Gallery, a corridor that rises at a precise angle through the heart of the pyramid, demonstrates masonry techniques that rival anything produced in the modern era. This passage is corbelled, meaning that each course of stone blocks extends slightly inward from the course below it, creating a gradually narrowing space that culminates in a flat ceiling nearly 30 feet above the floor. The corbelling technique used in the Grand Gallery required mathematical calculations that ensured structural stability while creating a passage of specific dimensions. Each block had to be shaped to exact specifications, with angles and dimensions calculated to contribute to the overall geometry of the corridor. The blocks interlock in complex three-dimensional patterns that distribute loads and prevent any individual stone from failing under the enormous pressures generated by the surrounding masonry. The surface finish of the Grand Gallery walls approaches perfection. The limestone blocks are fitted together so precisely that the joints between them are barely visible. The surfaces are smooth and flat to tolerances that challenge modern construction standards. The overall alignment of the passage maintains mathematical accuracy across a length of over 150 feet and a rise of nearly 90 feet. Creating passages of this precision within a growing pyramid required construction techniques that coordinated multiple complex operations simultaneously. The passage had to maintain proper alignment as the surrounding masonry was built up around it. The corbelling had to proceed at exactly the right rate to achieve the intended geometry. The surface finishing had to be completed while the passage remained accessible to workers and their tools. The ascending and descending passages that provide access to the chamber system demonstrate similar levels of precision and planning. These narrow tunnels, barely wide enough for a person to crawl through, maintain constant angles and dimensions across hundreds of feet of length. They were cut through solid limestone with such accuracy that their walls are straight and smooth, their dimensions consistent, and their alignments mathematically perfect. The construction of these passages required surveying techniques that could maintain accuracy across long distances through solid rock. Workers had to establish reference lines and control points that would guide the excavation process. They had to coordinate the work of multiple teams, cutting from different directions to ensure that the passages would meet at exactly the right time points with perfect alignment. The ventilation shafts that extend from the king's and queen's chambers to the outside of the pyramid represent another dimension of engineering sophistication. These narrow channels, only 8 inches square in cross-section, extend for hundreds of feet through the solid masonry of the pyramid. They maintain constant dimensions and precise alignments, despite following complex three-dimensional paths that navigate around other structural elements. The purpose of these shafts has been debated for decades, but their construction requirements are undeniable. Creating straight, smooth channels through hundreds of feet of solid masonry required drilling and cutting techniques that could maintain accuracy across enormous distances. The channels had to be planned and executed as integral parts of the pyramid's construction, coordinated with all the other structural elements to ensure they would reach their intended destinations. The mathematical precision embedded throughout the pyramid's internal structure reveals planning and design capabilities that challenge every assumption about ancient engineering. The passages align with specific astronomical targets, pointing towards stars and constellations that held religious significance for the ancient Egyptians. The chamber dimensions incorporate mathematical relationships that demonstrate sophisticated understanding of geometry and proportion. The king's chamber, for example, has length, width, and height dimensions that relate to each other through mathematical ratios found throughout nature. The proportions of the chamber create acoustic properties that generate specific resonant frequencies when sounds are produced within the space. Whether these acoustic effects were intentional or accidental, they demonstrate the complex interactions between geometry, materials, and physics that the ancient builders somehow managed to coordinate. The Queen's Chamber, despite its name actually having no connection to any queen, presents its own engineering challenges. Located at a different level within the pyramid and accessed through a separate passage system, this chamber required coordination with the overall construction sequence while maintaining its own structural integrity. The chamber features unfinished elements that provide clues about construction techniques, including tool marks that reveal the methods used to shape and smooth the limestone walls. The subterranean chamber, carved directly into the bedrock beneath the pyramid, demonstrates yet another set of engineering capabilities. This underground room required excavation techniques that could remove solid rock while maintaining structural stability. The chamber had to be positioned precisely in relation to the pyramid above it, requiring surveying methods that could coordinate surface and underground construction activities. The integration of all these internal elements within the overall pyramid structure required three-dimensional planning and coordination that rivals modern architectural and engineering practice. Every chamber, passage, and structural element had to be positioned exactly right in relation to every other element. The construction sequence had to proceed in precisely the right order to ensure that all the internal features could be completed while the external structure was being built around them. The precision of this coordination becomes apparent when you consider the alternatives. If the internal chambers had been even slightly misaligned, the structural systems wouldn't have worked correctly. If the passages had deviated from their intended paths, they wouldn't have connected properly with the chambers they were meant to serve. If the construction sequence had been wrong, it would have been impossible to install the massive granite blocks in the king's chamber or complete the complex masonry work in the relieving chambers. The quality control systems required to maintain this precision throughout the construction process demonstrate administrative and technical capabilities that challenge our understanding of ancient organizational systems. Every element had to be measured, verified, and approved before construction could proceed to the next phase. Errors had to be detected and corrected before they could propagate through the structure and create larger problems. The workforce coordination required for this internal construction was as complex as any aspect of the pyramid building process. Different teams had to work simultaneously on chamber construction, passage excavation, and external masonry, all while maintaining precise coordination to ensure that their work would integrate correctly. Materials had to be delivered to specific locations within the growing structure at exactly the right times. Specialized craftsmen had to be available when their particular skills were needed for critical operations. The evidence for this sophisticated internal construction challenges every theory that attempts to explain pyramid building through simple or primitive methods. The level of precision, the complexity of the structural systems, and the coordination required for successful completion all point to engineering and organizational capabilities that were far more advanced than traditional historical accounts have recognized. As we examine the final phases of pyramid construction, we'll discover even more evidence for the remarkable sophistication of ancient Egyptian engineering. The techniques used to create the smooth outer surfaces, install the precision-fitted casing stones, and complete the pyramidion that crowned the entire structure, reveal capabilities that push ancient technology to its absolute limits, while maintaining the mathematical and structural perfection that has allowed these monuments to survive for millennia. The completion of the pyramid's exterior required construction techniques that transformed the stepped core structure into the smooth-sided geometric perfection we associate with these ancient monuments. This final phase of construction presented challenges that were different from, but no less demanding than, the internal work we've already explored. The casing stones that covered the entire exterior of the pyramid were cut from the finest white limestone available, quarried from deposits across the Nile River from Giza. These blocks were shaped to create perfectly smooth, flat surfaces that would fit together with joints so tight that the completed pyramid surface appeared to be carved from a single piece of stone. The precision required for this casing work exceeds anything found in modern construction. Each casing stone had to be cut to exact specifications that would allow it to fit perfectly with its neighbors while contributing to the overall geometric accuracy of the pyramid's faces. The blocks were shaped with complex three-dimensional angles that varied depending on their position within the structure. Corner blocks required the most sophisticated cutting, as they had to interface correctly with casing stones on two different faces of the pyramid, while maintaining the precise angles necessary for geometric perfection. The installation of these casing stones required lifting and positioning techniques that could handle blocks weighing several tons, while maintaining the precision necessary for perfect fit. The stones couldn't simply be placed approximately and then adjusted. They had to be positioned exactly right the first time, because any significant adjustments would damage the precisely cut surfaces and compromise the tight joints that were essential for the casing system to work correctly. The surface preparation required before casing stone installation was itself a major engineering undertaking. The stepped core of the pyramid had to be prepared to receive the casing stones, with surfaces cut and shaped to provide perfect support for the final exterior blocks. This preparation work required the same precision and attention to detail as the casing stones themselves, because any irregularities in the core surface would prevent the casing stones from fitting correctly. The mathematical precision of the completed casing work was extraordinary. The four faces of the pyramid rose at exactly the same angle, meeting at a point nearly 500 feet above the base. The edges where adjacent faces met were perfectly straight lines that extended from the base corners to the apex without any deviation. The surface of each face was perfectly flat, creating smooth planes that reflected sunlight like enormous mirrors. The tools and techniques required for this precision casing work represent the pinnacle of ancient stone-cutting technology. The Egyptians developed cutting methods that could create flat surfaces accurate to within fractions of an inch across blocks spanning several feet. They created finishing techniques that could polish limestone to smoothness that rivals modern machine work. They manufactured measuring and alignment tools that could ensure perfect fit between blocks weighing tons. The coordination required to complete the casing work successfully was as complex as any aspect of pyramid construction. The casing stones had to be cut to exact specifications at quarry sites, transported without damage to the construction area, lifted to their proper positions at considerable heights above ground level, and installed with perfect precision to create the smooth exterior surfaces. The quality control systems required for casing stone work had to catch and correct errors that could compromise the entire exterior finish. A single improperly cut or incorrectly positioned casing stone could create problems that would affect the fit of numerous surrounding blocks. The inspection and approval procedures had to verify not just the individual quality of each stone, but also its proper integration with the overall casing system. The completion of the pyramid required installing a capstone, or pyramidion, at the very apex of the structure. This final element had to be shaped and positioned with extraordinary precision to complete the geometric perfection of the entire monument. The pyramidion was often made from a single piece of granite or other hard stone, cut and polished to create the perfect point that crowned the pyramid. Installing the pyramidion required lifting techniques that could handle substantial weight at a height of nearly 500 feet above ground level. The positioning had to be exact because the pyramidion served as the final reference point for the geometric accuracy of the entire structure. Any deviation in its position would be visible as an imperfection in the pyramid's profile when viewed from a distance. The completed pyramid represented an achievement in precision construction that wouldn't be equaled for thousands of years. The geometric accuracy of the structure, the precision of the stonework, and the sophistication of the engineering solutions all demonstrate capabilities that challenge our understanding of ancient technology and organization. The survival of these monuments for over 4 millennia provides ongoing testimony to the quality of the construction methods and materials used in their creation. The structural systems continue to function correctly, supporting the enormous loads for which they were designed. The precision of the original construction remains evident in measurements taken with modern instruments. The engineering solutions continue to impress contemporary architects and engineers who study these ancient achievements. The evidence for sophisticated ancient engineering capabilities extends far beyond the pyramids themselves. The infrastructure required to support pyramid construction, from quarries and transportation systems to worker villages and administrative facilities, demonstrates organizational and technical capabilities that rival modern industrial operations. The institutional knowledge required to plan, design, and execute these projects represents intellectual achievements that challenge every assumption about the limitations of ancient civilizations. The techniques developed for pyramid construction influenced Egyptian engineering for centuries afterward, appearing in temples, tombs, and other monumental structures throughout the ancient world. The knowledge and skills demonstrated in pyramid building represent not isolated achievements, but the products of sophisticated engineering traditions that developed over generations of accumulated experience and innovation. The legacy of pyramid construction techniques extends to modern engineering and construction practices. Contemporary architects and engineers study ancient methods not just for historical interest, but for practical insights that can inform modern projects. The principles of precision construction, quality control, and project coordination demonstrated in pyramid building remain relevant to large-scale construction projects today. As we conclude our exploration of pyramid construction methods, the evidence overwhelmingly demonstrates that these monuments were built using sophisticated engineering techniques implemented by highly skilled and well-organized human societies. No extraterrestrial intervention was required because human ingenuity, when supported by adequate resources and institutional knowledge, is capable of achievements that seem impossible to later generations who have lost the techniques and forgotten the capabilities of their ancestors. The ancient Egyptians who built the pyramids were not primitive people guided by alien visitors. They were accomplished engineers, skilled craftsmen, and organizational masters who developed revolutionary solutions to unprecedented engineering challenges. Their achievements represent the pinnacle of human capability applied to monumental construction projects that continue to inspire awe and admiration more than 4,000 years after their completion. The tools that made pyramid construction possible represent a technological revolution that transformed simple materials into precision instruments capable of shaping the hardest stone. When modern engineers examine the copper chisels, bronze saws, and wooden implements found at pyramid sites, they're often surprised by their effectiveness and sophistication. Copper, the primary metal available to pyramid builders, might seem inadequate for cutting limestone and granite, but the ancient Egyptians understood metallurgy in ways that maximized their tools' capabilities. They developed copper alloys that were significantly harder than pure copper, incorporating tin and other elements to create cutting edges that could maintain their sharpness through extended use. More importantly, they understood the process of work hardening, repeatedly hammering and annealing their tools to achieve optimal hardness and durability. The bronze saws used for cutting granite blocks were marvels of ancient engineering. These weren't simple metal blades trying to cut through stone by brute force. Instead, they functioned as delivery systems for abrasive compounds that did the actual cutting. The saw teeth trapped particles of quartz sand, creating an abrasive slurry that could wear through even the hardest granite when applied with patience and skill. Archaeological experiments have demonstrated the remarkable effectiveness of these ancient cutting methods. Modern researchers using replica bronze saws and quartz sand abrasives have successfully cut through granite blocks, achieving straight cuts modern machine work. The key and smooth surfaces that rival insight is that these tools require different techniques than modern cutting implements, but when used correctly, they could achieve extraordinary precision. The wooden implements used in pyramid construction were equally sophisticated, though their organic nature means fewer examples have survived to the present day. The wooden rollers, sleds, and lever systems represented mechanical engineering solutions that multiplied human force through clever application of physics principles. These weren't crude tree branches pressed into service, but carefully designed and manufactured tools created specifically for moving massive stone blocks. The sleds used for transporting pyramid blocks incorporated advanced understanding of friction, weight distribution, and structural engineering. The runners were shaped to specific profiles that minimized resistance while maximizing stability. The platforms were designed to distribute loads evenly, preventing damage to both the blocks being transported and the sleds themselves. Some sleds included sophisticated rope and pulley arrangements that provided mechanical advantage for the teams pulling them. The measuring and surveying instruments used by pyramid builders achieved accuracy that rivals modern precision tools. The Egyptian royal cubit, standardized at approximately 20.5 inches, remained consistent across the entire construction project and throughout the broader Egyptian kingdom. This standardization required manufacturing capabilities that could produce measuring rods accurate to fractions of an inch and quality control systems that maintained these standards across thousands of individual tools. The plumb bobs used for establishing vertical references were weighted with lead or dense stone to provide reliable performance even in windy conditions. The strings or cords attached to these weights were made from twisted flax fibers that provided strength and minimal stretch, ensuring that vertical measurements remained accurate throughout the construction process. Some plumb bobs included adjustable features that allowed fine-tuning of their performance for specific applications. The water levels used for establishing horizontal references demonstrated sophisticated understanding of hydrostatic principles. These weren't simple containers filled with water, but carefully designed instruments that could detect minute variations in elevation across considerable distances. Some included graduated scales that allowed precise measurement of height differences, while others incorporated sighting devices that enhanced their accuracy for long-distance surveying work. The rope and cordage used throughout pyramid construction represented another area of advanced ancient technology. The fibers had to be strong enough to handle extreme loads, while remaining flexible enough for complex rigging arrangements. The ancient Egyptians developed sophisticated rope-making techniques that created cordage with predictable strength characteristics and minimal stretch under load. The quality control systems that governed tool production and maintenance were as important as the tools themselves. Every chisel had to maintain its cutting edge throughout long periods of use. Every measuring rod had to remain accurate despite handling by numerous workers. Every rope had to perform reliably under extreme loads that could cause catastrophic failure if the cordage proved inadequate. The workshops that produced these tools were themselves engineering marvels, featuring specialized equipment for metalworking, woodworking, and rope production. The copper smelting facilities had to maintain precise temperatures for alloying and heat treatment. The woodworking shops required seasoned timber and precision cutting tools. The rope works needed facilities for processing plant fibers and twisting them into high-strength cordage. The logistics of tool distribution and maintenance across the massive pyramid construction project required administrative systems that tracked thousands of individual items. Tools had to be delivered to specific work crews at the right times. Damaged or worn tools had to be collected, repaired or replaced, and returned to service. Quality standards had to be maintained consistently across all tool production and maintenance activities. The training required for workers to use these tools effectively was extensive and specialized. Stone cutting required understanding of how different types of rock responded to various cutting techniques. Transportation work demanded knowledge of rigging, load distribution, and coordinated team movements. Surveying and measurement work required mathematical skills and understanding of geometric principles. The evolution of tool technology throughout the pyramid construction period shows continuous improvement and refinement. Early tools were simpler and less specialized, while later implements incorporated lessons learned from years of practical experience. This technological development demonstrates the innovative capacity of ancient Egyptian craftsmen and their commitment to continuous improvement. The preservation of tool-making knowledge across generations required sophisticated training and apprenticeship systems. Master craftsmen had to pass their knowledge to younger workers who would eventually become the next generation of toolmakers and users. This knowledge transfer process ensured that technological capabilities continued to advance rather than being lost when individual craftsmen retired or died. The seasonal nature of pyramid construction, with work intensifying during the Nile flood season, created additional challenges for tool management. Huge numbers of tools had to be produced and maintained during peak construction periods, then properly stored and maintained during slower periods. This cyclical demand required production planning and inventory management systems that could anticipate future needs and ensure adequate supplies were available when required. The specialization of tools for different construction tasks reveals the sophisticated understanding ancient Egyptians had developed about the relationship between tools and techniques. Quarrying tools were different from transportation tools, which were different from precision finishing tools. Each category required specific materials, manufacturing methods, and maintenance procedures optimized for its particular applications. The standardization of tools across the entire pyramid construction project ensured compatibility and interchangeability that simplified logistics and maintenance. A chisel produced in one workshop could be used by workers trained in different locations. Measuring rods from different sources would give consistent readings. This standardization required quality control systems and manufacturing specifications that were remarkably advanced for their time. The economic systems that supported tool production and distribution represented a significant fraction of the resources devoted to pyramid construction. The copper had to be mined, smelted, and worked into tools. The wood had to be harvested, seasoned, and shaped. The plant fibers had to be processed into rope and cordage. All of these activities required skilled workers, specialized facilities, and administrative oversight. The environmental challenges of working in the Egyptian desert placed additional demands on tool performance and maintenance. The heat, sand, and dry conditions could cause rapid deterioration of organic materials, while creating maintenance challenges for metal tools. The ancient Egyptians developed preservation and maintenance techniques that allowed their tools to function effectively despite these harsh conditions. The archaeological evidence for ancient Egyptian tool technology continues to expand our understanding of their capabilities. Recent discoveries have revealed tools and manufacturing techniques that were more sophisticated than previously recognized. Advanced metallurgical analysis has shown that ancient copper alloys were more complex and effective than simple historical accounts suggested. The influence of pyramid construction tool technology extended far beyond the immediate construction projects. The techniques developed for pyramid building influenced tool-making throughout Egyptian trade and cultural exchange. The legacy of these civilizations and spread to other ancient cultures through engineering and construction. The integration of tool technology with construction techniques created synergistic effects that multiplied. The innovations can be traced through subsequent developments in ancient effectiveness of both. Tools designed specifically for pyramid construction methods achieved performance levels that wouldn't have been possible with generic implements. Construction techniques optimized for available tool capabilities achieved precision and efficiency that maximize the potential of the technology. The comparison between ancient Egyptian tools and modern construction implements reveals both similarities and differences that illuminate the development of technology over time. While modern tools often rely on powered machinery and advanced materials, the fundamental principles of cutting, lifting, and measuring remain surprisingly consistent. The ancient Egyptians achieved remarkable results by optimizing their tools for human power sources and available materials. The preservation and study of ancient tools provides ongoing insights into the capabilities and limitations of historical technology. Archaeological experiments using replica tools continue to reveal new information about ancient construction techniques and expand our appreciation for the sophistication of early engineering solutions. The organizational systems that coordinated tool production, distribution, and maintenance across the massive scale of pyramid construction projects demonstrate administrative capabilities that rival modern industrial operations. The ancient Egyptians successfully managed the complex logistics of keeping thousands of workers supplied with properly maintained tools throughout construction projects that lasted for decades. The innovation and continuous improvement evident in ancient Egyptian tool technology challenges assumptions about technological stagnation in ancient civilizations. The pyramid builders were not simply using inherited techniques without modification, but were actively developing new solutions and refining existing methods to meet the unprecedented challenges of their monumental construction projects. The legacy of ancient Egyptian tool technology extends to modern engineering and construction practices. Contemporary toolmakers and users can learn from the principles and techniques developed by ancient craftsmen who achieved remarkable results with limited materials and power sources. The ingenuity and precision of ancient tool design continues to inspire modern innovations in construction technology. As we transition from examining the tools and techniques to understanding the broader implications of pyramid construction, the evidence becomes overwhelming that these monuments represent the pinnacle of human achievement rather than evidence of extraterrestrial intervention. The sophistication of the tools, the precision of the techniques, and the complexity of the organizational systems all point to human capabilities that were far more advanced than traditional historical accounts have recognized. The mystery of pyramid construction dissolves when we examine the evidence with proper appreciation for ancient Egyptian ingenuity and determination. These weren't primitive people stumbling toward accidental greatness with alien assistance. They were accomplished engineers and skilled craftsmen who developed revolutionary solutions to unprecedented challenges through human intelligence, creativity, and organized effort applied at the highest levels of capability. The evidence for sophisticated pyramid construction becomes even more compelling when we examine the astronomical knowledge that guided these ancient engineers. The precision with which the Great Pyramid aligns with true north isn't just impressive, it's mathematically extraordinary. We're talking about an accuracy that deviates by less than 3/60ths of a degree, a level of precision that would challenge modern surveyors using GPS technology. To achieve this alignment, the ancient Egyptians had to develop surveying techniques that could determine true north with extraordinary accuracy. They couldn't simply use a magnetic compass, because magnetic north varies from true north and changes over time. Instead, they relied on astronomical observations that required sophisticated understanding of celestial mechanics and the rotation of the Earth. The method they most likely used involved observing circumpolar stars, those stars that appear to circle around the north celestial pole throughout the night. By tracking the movement of these stars and identifying the center point around which they rotate, ancient astronomers could establish true north with remarkable precision. This wasn't casual stargazing. It required systematic observations conducted over extended periods, mathematical calculations to determine the center of rotation, and surveying techniques to translate celestial observations into terrestrial construction references. The star that served as the North Star during pyramid construction wasn't Polaris, which holds that position today. Instead, it was Thuban, a star in the constellation Draco that occupied the position closest to the North Celestial Pole around 2500 BCE. The descending passage in the Great Pyramid points directly toward where Thuban would have appeared in the night sky, creating a connection between the pyramid's internal structure and the celestial sphere that guided its construction. But the astronomical sophistication of pyramid builders extends far beyond simple directional alignment. The dimensions and proportions of the Great Pyramid encode mathematical relationships that demonstrate advanced understanding of geometry and possibly even knowledge of fundamental mathematical constants that wouldn't be formally described until thousands of years later. The relationship between the pyramid's height and the perimeter of its base approximates the mathematical constant pi with remarkable accuracy. Whether this was intentional or resulted from their construction methods remains debated, but the precision of this relationship suggests mathematical knowledge that challenges traditional assumptions about ancient capabilities. The pyramid's proportions also incorporate what appears to be the golden ratio, a mathematical relationship found throughout nature and considered aesthetically pleasing by cultures across history. These mathematical relationships weren't accidental byproducts of construction convenience. They required deliberate planning and sophisticated calculations that demonstrate understanding of geometric principles and mathematical relationships. The ancient Egyptians had to possess not just the theoretical knowledge of these mathematical concepts, but also the practical skills to implement them accurately in a construction project involving millions of stone blocks. The surveying techniques required to maintain these mathematical relationships throughout the construction process were themselves engineering marvels. The pyramid builders had to establish and maintain reference points that would ensure geometric accuracy across the entire structure. They needed measuring systems that could verify angles, distances, and elevations with precision that wouldn't accumulate errors as construction progressed. The baseline measurements for the pyramid had to be established with extraordinary accuracy because any errors in the foundation would compound as the structure grew taller. The ancient surveyors used techniques that could create a perfectly square base with sides differing by less than 2 inches across distances of over 700 feet. This level of accuracy required not just precise measuring tools, but also mathematical understanding of how to correct for the curvature of the Earth across such distances. The leveling of the pyramid's foundation presented challenges that pushed ancient engineering to its limits. The base had to be flat to within inches across an area covering more than 13 acres. To achieve this precision, the builders developed techniques using water-filled channels that served as level references. Water always seeks its own level, so by creating a network of interconnected channels across the construction site, they could establish elevation references that were accurate across the entire foundation area. This water leveling technique required sophisticated understanding of hydrostatic principles and careful engineering to ensure the channel system would provide reliable references. The channels had to be protected from disturbance during construction activities, while remaining accessible for measurement and verification throughout the leveling process. The system had to account for variations in water temperature that could affect the level readings and compensate for any settlement or movement in the foundation during construction. The precision of the foundation leveling becomes even more impressive when you consider the underlying geology. The Giza Plateau isn't perfectly flat bedrock. It includes natural variations and irregularities that had to be accommodated in the foundation design. The ancient engineers had to identify and compensate for these geological variations while maintaining the mathematical precision required for the pyramid's geometric accuracy. The construction sequence itself reveals planning capabilities that coordinated multiple complex operations across decades of construction activity. The pyramid couldn't be built in random order. Each phase had to be completed in precisely the right sequence to ensure that subsequent phases could be executed successfully. The internal chambers had to be constructed as the external structure grew around them. The casing stones had to be installed in coordination with the core masonry. The final finishing work had to proceed in a sequence that maintained access for workers and equipment while achieving the intended precision. This construction sequencing required project management skills that anticipated problems and coordinated solutions across multiple interdependent activities. The ancient project managers had to understand not just the technical requirements of each construction phase, but also the logistical challenges of coordinating materials, equipment, and workforce across the entire project timeline. The quality control systems that maintained precision throughout the construction process demonstrate administrative capabilities that rival modern industrial operations. Every block had to be inspected and approved before installation. Every measurement had to be verified against established references. Every construction phase had to meet specifications before subsequent work could proceed. The inspection procedures had to catch errors before they could propagate through the structure and create larger problems. A single misaligned block could affect the positioning of dozens of surrounding blocks. A foundation error could compromise the geometric accuracy of the entire pyramid. The quality control systems had to prevent these cascading failures while maintaining construction productivity across thousands of individual operations. The workforce coordination required for this level of precision involved training and supervision systems that ensured consistent performance across multiple shifts and seasonal work cycles. Workers had to understand not just their individual tasks, but also how their work integrated with the broader construction objectives. Supervisors had to maintain quality standards while managing productivity and safety across dangerous construction operations. The seasonal nature of pyramid construction, intensifying during the Nile flood when agricultural work was impossible, created additional coordination challenges. The workforce could expand dramatically during peak construction seasons, requiring training and integration systems that could quickly bring new workers up to the required skill levels. The construction activities had to be planned to take advantage of peak workforce availability while maintaining continuity during periods when fewer workers were available. The supply chain management required to support pyramid construction involved coordinating materials delivery from sources scattered across Egypt and beyond. Limestone came from local quarries. Granite travelled hundreds of miles from Aswan. Copper and other metals came from mining operations in the Eastern Desert and Sinai Peninsula. Wood for tools and construction equipment came from various sources, some requiring importation from other regions entirely. Each material had to arrive at the construction site in the right quantities at the right times. Storage and inventory management systems had to protect materials from damage while ensuring they remained accessible when needed. Transportation networks had to maintain reliable delivery schedules despite seasonal variations in river levels, weather conditions, and availability of transport crews. The economic systems that funded and supported pyramid construction represented a significant fraction of Egypt's total economic output during the construction period. The resources devoted to these projects included not just the direct costs of materials and labour, but also the indirect costs of supporting infrastructure, administrative systems, and the opportunity costs of diverting skilled workers from other productive activities. The economic impact extended throughout Egyptian society and beyond. Quarry operations employed thousands of workers and stimulated development of mining and stoneworking industries. Transportation systems created employment and infrastructure that benefited trade and commerce. The concentration of skilled craftsmen at construction sites created centres of technological innovation that influenced developments throughout the ancient world. The institutional knowledge required to plan, design, and execute pyramid construction projects represented intellectual achievements that took generations to develop and accumulate. The engineering techniques, organizational systems, and administrative procedures didn't emerge fully formed with the first pyramid project. They evolved through decades of experience, experimentation, and refinement across multiple construction projects. This institutional knowledge was preserved and transmitted through sophisticated training and apprenticeship systems that ensured continuity across generations of craftsmen and engineers. Master builders passed their knowledge to apprentices, who would eventually become the next generation of project leaders. The knowledge wasn't just technical information about construction techniques, but also included organizational wisdom about managing complex projects and coordinating large workforces. The preservation of this institutional knowledge required written records and administrative systems that documented successful techniques and procedures. Archaeological evidence shows that the ancient Egyptians maintained detailed records of construction activities, resource allocation, and workforce management. These records served not just as administrative tools for current projects, but also as reference materials for future construction activities. The technological innovations developed for pyramid construction influenced engineering and construction practices throughout the ancient world and across subsequent historical periods. The techniques for cutting and shaping stone, moving heavy loads, and achieving geometric precision found applications in temples, palaces, and other monumental construction projects throughout Egyptian civilization and beyond. The influence of pyramid construction technology extended through trade and cultural exchange to other ancient civilizations. The engineering principles and construction techniques developed at Giza influenced building practices in Nubia, the Levant, and other regions that maintained contact with Egyptian civilization. The legacy of these innovations can be traced through architectural developments across centuries of ancient history. The scientific principles embedded in pyramid construction demonstrate understanding of physics, mathematics, and engineering that was far more sophisticated than traditional historical accounts have recognized. The ancient Egyptians understood principles of structural mechanics, load distribution, and geometric relationships that wouldn't be formally described by academic disciplines until thousands of years later. This scientific knowledge wasn't theoretical understanding, divorced from practical application. It was integrated knowledge that combined mathematical principles with engineering techniques and organizational systems to achieve unprecedented construction objectives. The pyramid builders understood not just how to calculate geometric relationships, but also how to implement those calculations accurately in massive construction projects. The precision manufacturing capabilities demonstrated in pyramid construction reveal industrial techniques that challenge assumptions about ancient technological limitations. The cutting and shaping of stone blocks to tolerances measured in fractions of inches, the polishing of surfaces to near-mirror smoothness, and the fitting of joints so tight that modern tools cannot detect gaps all demonstrate manufacturing capabilities that rival modern precision work. These manufacturing techniques weren't isolated achievements in stoneworking. They were part of comprehensive technological systems that included metallurgy for tool production, chemistry for adhesives and preservation compounds, and physics for understanding the behavior of materials under stress and environmental conditions. The integration of all these technological, organizational, and intellectual achievements in pyramid construction projects represents human capability operating at extraordinary levels. The ancient Egyptians didn't just build impressive monuments. They developed and implemented technological and organizational systems that pushed the boundaries of what was possible with available resources and knowledge. The evidence overwhelmingly demonstrates that pyramid construction was achieved through human ingenuity, determination, and organized effort applied at the highest levels of capability. The sophistication of the engineering solutions, the precision of the construction techniques, and the complexity of the organizational systems all point to human achievements that were far more advanced than traditional historical accounts have recognized. The mystery dissolves when we examine pyramid construction with proper appreciation for ancient Egyptian capabilities. These monuments weren't built by primitive people with alien assistance. They were created by accomplished engineers, skilled craftsmen, and organizational masters who developed revolutionary solutions to unprecedented challenges through human intelligence and creativity, applied with unprecedented focus and resources. The legacy of pyramid construction continues to inspire and inform modern engineering and construction practices. Contemporary architects and engineers study ancient techniques not just for historical interest, but for practical insights that can enhance modern projects. The principles of precision construction, quality control, and project coordination demonstrated in pyramid building remain relevant to large-scale construction projects today. The human achievement represented by pyramid construction deserves recognition for what it actually was: the pinnacle of ancient engineering and organizational capability, applied to create monuments that have inspired awe and admiration for over 4,000 years. No extraterrestrial intervention was required, because human beings, when supported by adequate resources and institutional knowledge, are capable of achievements that seem impossible to later generations, who have forgotten the techniques and lost the capabilities of their ancestors. The ancient Egyptians who built the pyramids were not primitive people guided by alien visitors. They were the intellectual and technological equals of any civilization in human history, working with the materials and knowledge available to them to create monuments that continue to challenge our understanding of what human beings can accomplish when they dedicate themselves to pursuing the seemingly impossible with unwavering determination and sophisticated organization. The preservation of these monuments across more than 4 millennia provides perhaps the most compelling evidence for the sophistication of their construction methods. While countless other ancient structures have crumbled into dust, the pyramids continue to stand with their geometric precision intact, their structural systems functioning exactly as their designers intended. This extraordinary longevity wasn't accidental. It resulted from engineering decisions that demonstrate profound understanding of material science, structural mechanics, and environmental factors that would affect the monuments over geological timescales. The pyramid builders weren't just creating impressive structures for their own time. They were designing monuments intended to last forever, and they succeeded in ways that continue to astound modern engineers. The selection of limestone as the primary building material reveals sophisticated understanding of stone properties and long-term durability. The specific limestone beds chosen for pyramid construction had characteristics that made them ideal for monumental building. When first quarried, this limestone was relatively soft and easy to work, allowing precise cutting and shaping with available tools. But exposure to air and moisture caused chemical changes that hardened the stone over time, creating increasingly durable construction material as the centuries passed. This natural hardening process, combined with the massive scale of the construction, created structures that became more stable and resistant to weathering as they aged. The enormous weight of the pyramid actually contributes to its stability, compressing the lower courses and creating structural integrity that increases rather than decreases over time. Modern structural analysis confirms that the pyramids are more stable today than they were when construction was completed. The foundation systems demonstrate engineering foresight that anticipated problems and incorporated solutions that would function across millennia. The foundations extend deep into the bedrock, distributing the enormous loads across stable geological formations that can support the weight indefinitely. The foundation design also incorporates drainage systems that prevent water accumulation and the freeze-thaw cycles that destroy so many ancient structures in other climates. The jointing systems used throughout pyramid construction reveal understanding of how stone structures behave under long-term loading and environmental stress. The blocks were fitted together in patterns that distribute loads evenly and prevent the concentration of stresses that could cause structural failure. The joints were designed to accommodate the slight movements and settlements that occur in any large structure without compromising overall integrity. The absence of mortar in much of the construction wasn't a limitation of available technology, but a deliberate design choice that created superior long-term performance. Mortar joints can deteriorate over time, creating weak points that compromise structural integrity. The pyramid builders instead relied on precise cutting and fitting that created joints so tight that the blocks function as a monolithic structure. with load transfer occurring directly between stone surfaces, rather than through potentially degradable binding materials. The internal chamber systems demonstrate structural engineering principles that protected critical spaces from the enormous loads pressing down from above. The relieving chamber systems above the king's chamber continue to function perfectly after more than 4,000 years, distributing loads exactly as their designers intended. Modern structural analysis confirms that these systems incorporate principles of load distribution and stress concentration that weren't formally described by engineering science until the modern era. The acoustic properties of the internal chambers reveal another dimension of sophisticated design that may have been intentional or may represent fortunate consequences of precise geometric construction. The king's chamber generates specific resonant frequencies when sounds are produced within the space, creating acoustic effects that enhance the impact of ceremonial activities. Whether these acoustic properties were deliberately designed or accidentally achieved, they demonstrate the complex interactions between geometry, materials, and physics that the ancient builders somehow managed to coordinate successfully. The preservation of surface finishes on the remaining casing stones provides evidence for construction quality that exceeds modern standards in many respects. The surfaces are polished to smoothness that approaches optical flatness, with tool marks so fine that they're barely visible even under magnification. The joints between casing stones are so precise that detecting the boundaries between individual blocks requires careful examination, creating the appearance of structures carved from single pieces of stone. This surface quality wasn't achieved through simple handwork with primitive tools. It required systematic finishing processes that controlled every aspect of surface preparation, cutting, and polishing. The consistency of the surface quality across thousands of individual blocks demonstrates manufacturing capabilities and quality control systems that maintain standards throughout the entire construction project. The alignment precision of the completed pyramids provides ongoing testimony to the accuracy of the surveying and construction methods used by the ancient builders. Modern laser measurements confirm that the geometric relationships established during construction remain accurate to within fractions of degrees and inches across structures spanning hundreds of feet in every direction. This precision hasn't degraded significantly, despite millennia of environmental exposure, earthquake activity, and human interference. The mathematical relationships embedded in pyramid proportions continue to intrigue researchers who discover new connections between the structure's dimensions and fundamental constants of mathematics and physics. Whether these relationships were intentionally incorporated or represent consequences of construction methods optimized for other purposes, they demonstrate levels of precision that challenge every assumption about the limitations of ancient construction techniques. The environmental resilience of pyramid construction becomes apparent when you consider the harsh conditions these structures have endured. The Egyptian desert presents extreme temperature variations, from scorching daytime heat to surprisingly cold nighttime conditions. These thermal cycles create expansion and contraction stresses that destroy many types of construction over time. The pyramids have endured thousands of years of these thermal cycles without significant structural damage. The occasional earthquakes that affect the region have provided natural stress tests that confirm the structural integrity of pyramid construction. While earthquakes have damaged or destroyed countless other ancient structures throughout the region, the pyramids have remained essentially intact, demonstrating structural design that anticipated and accommodated seismic forces that the builders had no way to measure or predict scientifically. The resistance to weathering and erosion demonstrates material selection and construction techniques optimized for long-term durability. While wind-blown sand has eroded softer stones and sculptures throughout Egypt, the pyramid blocks have maintained their structural integrity and surface quality remarkably well. The construction methods created structures that become more resistant to erosion as they age, rather than progressively weakening over time. The human interference these monuments have endured provides another measure of their construction quality. Throughout history, various groups have attempted to dismantle pyramids to obtain building materials for other projects. The precision and quality of the construction made these dismantling efforts extremely difficult and largely unsuccessful. The blocks were fitted together so precisely, and the structures were so well engineered, that removing individual blocks without damaging them proved nearly impossible with the tools and techniques available to later civilizations. The scientific studies conducted on pyramid construction using modern analytical techniques continue to reveal new evidence for the sophistication of ancient methods. Ground-penetrating radar has identified previously unknown internal features that demonstrate even more complex structural systems than were visible from surface examination. Thermal imaging has revealed temperature variations that provide clues about internal construction techniques and the presence of additional chambers or structural elements. Chemical analysis of pyramid materials has identified construction compounds and preservation treatments that were more sophisticated than previously recognized. The ancient Egyptians developed chemical treatments that enhanced the durability of construction materials and created protective coatings that contributed to long-term preservation. These chemical technologies demonstrate understanding of materials science principles that weren't formally described until modern times. The ongoing archaeological research at pyramid sites continues to uncover evidence that expands our understanding of construction methods and organizational systems. Recent excavations have revealed workshop areas, storage facilities, and administrative buildings that supported pyramid construction. These discoveries provide insights into the industrial infrastructure required to support projects of such scale and complexity. The comparative analysis of pyramid construction with other ancient building projects reveals the unique achievements represented by these monuments. While other ancient civilizations created impressive structures, none achieved the combination of scale, precision, and durability that characterizes Egyptian pyramid construction. The pyramids represent not just impressive achievements within their historical context, but unprecedented accomplishments that weren't equaled for thousands of years. The influence of pyramid construction techniques on subsequent architectural developments can be traced through later Egyptian monuments and structures built by other ancient civilizations that maintained contact with Egypt. The engineering principles and construction methods developed for pyramid building influenced temple construction, palace architecture, and other monumental projects throughout the ancient world. The preservation of pyramid construction knowledge through institutional systems demonstrates the sophisticated educational and professional development programs that supported ancient Egyptian engineering capabilities. The knowledge wasn't held by individual master builders, but was systematically preserved and transmitted through organized training programs that ensured continuity across generations of craftsmen and engineers. The economic analysis of pyramid construction reveals the enormous investment these projects represented and the sophisticated resource management systems required to sustain such massive undertakings. The economic impact extended throughout Egyptian society and influenced trade relationships with neighboring civilizations that supplied specialized materials and skilled workers for construction projects. The social implications of pyramid construction demonstrate organizational capabilities that coordinated the efforts of tens of thousands of people across decades of construction activity. The successful completion of these projects required social systems that maintained worker motivation, resolved conflicts, and sustained productivity throughout extended construction periods that spanned multiple generations of workers. The technological innovations developed specifically for pyramid construction had applications that extended far beyond monumental building projects. The tools, techniques, and organizational methods developed for pyramid construction influenced manufacturing, transportation, and administrative systems throughout Egyptian civilization. These innovations contributed to Egypt's technological leadership in the ancient world and influenced developments in engineering and construction across subsequent historical periods. The intellectual achievements represented by pyramid construction include not just the technical knowledge required for engineering and construction, but also the mathematical, astronomical, and administrative knowledge that supported project planning and execution. The ancient Egyptians developed and applied knowledge systems that integrated multiple disciplines in ways that wouldn't be matched again for thousands of years. The artistic achievements embedded in pyramid construction demonstrate that these weren't purely utilitarian projects, but represented conscious efforts to create monuments that would inspire awe and admiration. The geometric perfection, surface quality, and overall aesthetic impact of the completed pyramids reveal artistic sensibilities that were integrated with engineering requirements to create structures that function both as technical achievements and as works of monumental art. The symbolic significance of pyramid construction within ancient Egyptian culture demonstrates the integration of technological capability with religious and cultural objectives. The pyramids weren't just impressive demonstrations of engineering skill, but were designed to serve specific cultural and religious functions that required both technical precision and symbolic meaning. The legacy of pyramid construction continues to influence modern engineering and construction practices. Contemporary architects and engineers study ancient techniques not just for historical interest, but for practical insights that can inform modern projects. The principles of precision construction, quality control, and project coordination demonstrated in pyramid building remain relevant to current large-scale construction challenges. The inspiration provided by pyramid construction extends beyond technical applications to broader questions about human potential and achievement. These monuments demonstrate what human beings can accomplish when they combine advanced knowledge with sustained effort and adequate resources. They provide evidence that challenges assumptions about the limitations of human capability and the trajectory of technological development throughout history. The mysteries that remain about pyramid construction continue to drive research and investigation that advances our understanding of ancient capabilities and techniques. While we now understand the basic methods used for pyramid construction, many details remain unclear, providing ongoing opportunities for archaeological research and experimental reconstruction that expand our knowledge of ancient engineering and organizational systems. The comparison between ancient and modern construction capabilities reveals both the continuity and the differences in human engineering achievement across historical periods. While modern construction benefits from powered machinery and advanced materials, the fundamental challenges of precision construction, project coordination, and quality control remain essentially unchanged. The ancient Egyptians achieved remarkable results by optimizing human-powered techniques and available materials to levels that rival modern achievements in many respects. The evidence for sophisticated ancient construction capabilities challenges popular misconceptions about technological progress and the development of human civilization. The pyramid builders weren't primitive people who accidentally achieved impressive results through trial and error. They were accomplished engineers and skilled craftsmen who developed systematic approaches to unprecedented construction challenges and achieved results that demonstrate technological and organizational capabilities that were far more advanced than traditional historical accounts have recognized. The human story revealed through pyramid construction is ultimately more impressive than any alternative explanation involving extraterrestrial intervention or lost advanced civilizations. The monuments represent human intelligence, creativity, and determination, applied at the highest levels of capability to achieve objectives that seemed impossible even to the people attempting them. They demonstrate that human beings, when supported by adequate knowledge and resources, are capable of achievements that continue to inspire awe and admiration thousands of years after their completion. As we reach toward concluding our exploration of how the pyramids were actually built, the overwhelming evidence points to a simple but profound truth. These monuments represent the pinnacle of human achievement in engineering, organization, and construction. They were built by people who were every bit as intelligent and capable as modern engineers, working with the materials and knowledge available to them to create structures that continue to challenge our understanding of what human beings can accomplish when they dedicate themselves to pursuing ambitious objectives with sophisticated planning and unwavering determination. The ancient Egyptians who built the pyramids deserve recognition not as primitive people guided by alien visitors, but as the intellectual and technological pioneers who developed revolutionary solutions to unprecedented challenges through human ingenuity, operating at its absolute peak. Their achievements stand as permanent testimony to the potential of human capability when applied with adequate resources, institutional knowledge, and the determination to achieve what seems impossible. No aliens were required because human beings, when working at their intellectual and organizational best, are capable of creating monuments that seem miraculous to later generations who have forgotten the techniques and lost the institutional knowledge that made such achievements possible. The real mystery isn't how the pyramids were built, but how subsequent civilizations managed to lose the sophisticated engineering and organizational capabilities that made pyramid construction possible in the first place. The scale of administrative complexity required to sustain pyramid construction over decades reveals organizational systems that operated with efficiency and precision that would impress modern corporate managers. We're not talking about simple work gangs dragging stones across the desert. This was a sophisticated industrial operation that coordinated multiple supply chains, managed seasonal workforce fluctuations, and maintained quality standards across thousands of interdependent activities. Consider the inventory management challenges alone. The Great Pyramid required approximately 2.5 million individual stone blocks, each cut to specific dimensions and delivered to precise locations within the growing structure. Every single block had to be tracked from quarry to final installation, with records maintaining information about size, weight, intended position, and quality specifications. A single misplaced block could disrupt construction sequences and create delays that affected thousands of other operations. The ancient Egyptians developed record-keeping systems that tracked not just materials, but also workforce assignments, tool distribution, food production, and construction progress. Archaeological evidence shows that they maintained detailed inventories written on papyrus and carved into stone, documenting everything from daily bread rations to the completion status of specific construction phases. These weren't casual notes scribbled by foremen. They were comprehensive administrative records that enabled project managers to coordinate activities across the entire construction operation. The seasonal nature of pyramid construction created additional administrative challenges that required sophisticated planning and resource management. During the annual Nile flood, when agricultural work became impossible, the workforce could expand from a core team of several thousand permanent workers to populations approaching 30,000 people. This dramatic workforce expansion had to be planned, coordinated, and managed without disrupting ongoing construction activities or compromising quality standards. Housing this enormous seasonal workforce required infrastructure planning that anticipated needs months in advance. Archaeological excavations have revealed planned worker cities with organized streets, standardized housing units, communal dining facilities, and even entertainment areas. These weren't temporary camps thrown together haphazardly. They were planned communities designed to house, feed, and support tens of thousands of people in conditions that maintained health, productivity, and morale throughout extended construction seasons. The food production and distribution systems required to sustain this workforce represent logistical achievements that rival modern military operations. Recent archaeological analysis of animal bones and plant remains from worker villages reveals that pyramid builders consumed enormous quantities of beef, bread, beer, and other foods. The daily food requirements for 30,000 workers would have demanded agricultural production from vast areas of Egyptian farmland, along with transportation and storage systems capable of delivering fresh food to construction sites on a daily basis. The beer production alone required industrial-scale brewing operations that could produce thousands of gallons daily. Archaeological evidence shows that worker villages included multiple breweries with sophisticated fermentation systems and quality control procedures. The ancient Egyptians understood that beer wasn't just a beverage for pyramid workers. It was a crucial source of calories and nutrition that helped sustain the enormous physical demands of moving multi-ton stone blocks in desert heat. The medical care systems that supported pyramid construction workers demonstrate organizational concern for worker welfare that challenges traditional assumptions about ancient labor practices. Archaeological examination of worker burials has revealed evidence of sophisticated medical treatment, including successful bone setting, surgical procedures, and dental care. Workers who were injured on the job received medical attention that enabled many to return to productive work rather than being discarded as expendable labor. The tool production and maintenance systems required to keep thousands of workers equipped with properly functioning implements created additional administrative challenges. Copper chisels had to be repeatedly resharpened and annealed to maintain their cutting effectiveness. Bronze saws required replacement of worn cutting edges and periodic replacement of entire blades. Wooden implements needed repair and replacement as they wore out or broke under the stresses of heavy construction work. The coordination of specialized work teams reveals organizational sophistication that anticipated modern industrial management techniques. Different teams were responsible for quarrying, transportation, lifting, positioning, and finishing work. Each team required specialized tools, specific training, and coordination with other teams to ensure that their work integrated properly with overall construction objectives. Team leaders had to understand not just their own operations, but also how their work affected and depended on the activities of other specialized teams. The quality control systems that maintained construction precision throughout decades of work involved inspection procedures and approval processes that ensured every element met specifications before construction could proceed to subsequent phases. These weren't casual visual inspections by individual supervisors. They were systematic verification procedures that checked dimensions, alignment, surface quality, and structural integrity against established standards. The communication systems required to coordinate activities across the massive construction site had to function reliably despite the noise, dust, and physical obstacles that characterized active construction areas. Archaeological evidence suggests that the ancient Egyptians developed signaling systems using flags, horns, and other devices that could transmit information across considerable distances. Work coordination required communication methods that could synchronize the activities of multiple teams working simultaneously on different aspects of construction. The training and skill development systems that prepared workers for specialized construction tasks reveal educational capabilities that ensured consistent performance across the entire workforce. New workers had to learn not just basic construction techniques, but also safety procedures, quality standards, and coordination methods that enabled them to work effectively as part of larger teams. Master craftsmen developed apprenticeship programs that preserved and transmitted specialized knowledge across generations of workers. The transportation infrastructure that supported pyramid construction extended far beyond the construction site itself to include improved roads, river ports, and storage facilities that enabled efficient movement of materials from sources scattered across Egypt and beyond. The ancient Egyptians built dedicated transportation networks, optimized for moving heavy loads across considerable distances, with engineered roadways that could handle the extreme weights and traffic volumes generated by pyramid construction. The procurement systems that acquired materials from distant sources demonstrate commercial relationships and trade networks that extended throughout the ancient Mediterranean world. Granite from Aswan, copper from Sinai, and wood from Lebanon all had to be negotiated, purchased, and delivered according to construction schedules that coordinated material arrivals with workforce availability and construction sequences. The financial systems that funded pyramid construction involved economic planning and resource allocation that represented significant fractions of Egypt's total economic output during construction periods. The ancient Egyptians had to balance the enormous costs of pyramid construction against other national priorities while maintaining economic stability and social cohesion throughout construction periods that could last for decades. The technological development systems that supported continuous improvement in construction methods reveal innovative capabilities that refine techniques and develop new solutions throughout extended construction periods. The pyramid builders weren't simply applying inherited knowledge without modification. They were actively experimenting with new approaches and incorporating lessons learned from previous projects into current construction activities. The risk management systems that anticipated and planned for potential problems demonstrate foresight and contingency planning that minimize the impact of inevitable challenges on overall construction progress. Ancient project managers had to plan for equipment failures, material shortages, weather delays, and workforce problems while maintaining construction schedules and quality standards. The environmental protection measures that preserved construction sites and materials from weather damage reveal understanding of environmental factors and their effects on construction activities. The ancient Egyptians developed techniques for protecting work areas from sandstorms, preserving materials from moisture damage, and maintaining construction quality despite extreme temperature variations and other environmental challenges. The legacy preservation systems that documented construction methods and organizational procedures ensured that knowledge gained through pyramid construction would be available for future projects. The ancient Egyptians understood that the institutional knowledge developed through pyramid construction represented valuable intellectual assets that should be preserved and transmitted to future generations of engineers and craftsmen. The integration of all these administrative systems into comprehensive project management capabilities represents organizational achievement that rivals anything found in modern industrial operations. The ancient Egyptians successfully coordinated thousands of people, managed complex supply chains, maintained quality standards, and achieved construction objectives that required precision and coordination across unprecedented scales of activity. The evidence for this administrative sophistication challenges every assumption about the limitations of ancient organizational capabilities. The pyramid builders weren't primitive people struggling to coordinate simple construction activities through informal leadership and casual communication. They were accomplished administrators who developed systematic approaches to project management challenges that wouldn't be matched again for thousands of years. The success of pyramid construction projects demonstrates that ancient civilizations possessed organizational knowledge and administrative capabilities that enabled them to achieve objectives that seem impossible when viewed from modern perspectives that underestimate ancient capabilities. The monuments stand as permanent testimony not just to ancient engineering achievements, but also to the sophisticated organizational systems that made those engineering achievements possible. The workforce management systems that coordinated the activities of tens of thousands of people across multiple years of construction activity reveal leadership and administrative capabilities that challenge traditional assumptions about ancient management techniques. The successful completion of pyramid construction required organizational systems that motivated workers, maintained productivity, resolved conflicts, and sustained coordination across enormous teams of people working on dangerous and demanding construction tasks. The economic impact of pyramid construction extended throughout Egyptian society and influenced development patterns that shaped ancient civilization for centuries. The concentration of skilled craftsmen at construction sites created centers of technological innovation that influenced developments throughout the ancient world. The transportation networks developed to support pyramid construction facilitated trade and commerce that contributed to Egypt's economic prosperity and political influence. The cultural significance of pyramid construction within ancient Egyptian society demonstrates the integration of technological capability with religious and social objectives that gave these projects meaning and importance beyond their impressive engineering achievements. The pyramids weren't just monuments to royal power or demonstrations of engineering skill. They were expressions of cultural values and religious beliefs that motivated entire civilizations to devote enormous resources to their completion. The international influence of pyramid construction techniques and organizational methods spread through trade and cultural exchange to other ancient civilizations that adapted Egyptian innovations to their own construction projects and administrative challenges. The legacy of pyramid construction can be traced through architectural and organizational developments across centuries of ancient history and multiple civilizations. The preservation of pyramid construction knowledge through institutional systems demonstrates educational and professional development capabilities that maintain technological and organizational competence across generations of craftsmen and administrators. The knowledge wasn't lost when individual master builders retired or died, but was systematically preserved and transmitted through organized programs that ensured continuity of capability across extended historical periods. The modern relevance of ancient organizational achievements becomes apparent when contemporary project managers study pyramid construction methods and administrative systems for insights that can inform current large-scale construction projects. The principles of workforce coordination, quality control, and resource management demonstrated in pyramid construction remain applicable to modern industrial operations that face similar challenges of scale, complexity, and coordination. The scientific analysis of pyramid construction using modern analytical techniques continues to reveal new evidence for the sophistication of ancient methods and organizational systems. Advanced imaging technologies, chemical analysis, and computer modeling provide insights into construction techniques and administrative capabilities that weren't apparent from surface examination of the completed monuments. The archaeological research that continues at pyramid sites expands our understanding of the infrastructure and organizational systems that supported construction activities. Recent discoveries of workshop areas, administrative buildings, and worker settlements provide evidence for industrial capabilities and management systems that were more sophisticated than previously recognized. The comparative analysis of pyramid construction with other ancient building projects reveals the unique organizational achievements represented by these monuments. While other ancient civilizations created impressive structures, none achieved the combination of scale, precision, and administrative complexity that characterizes Egyptian pyramid construction projects. The human story revealed through analysis of pyramid construction, organizational systems, demonstrates capabilities that deserve recognition as achievements in their own right, separate from but equal in importance to the engineering and construction achievements they made possible. The ancient Egyptians developed management and administrative techniques that enabled them to coordinate human effort on scales that wouldn't be matched again until the industrial age. The evidence overwhelmingly demonstrates that pyramid construction was achieved through sophisticated organizational systems implemented by highly capable administrators who understood principles of project management, resource allocation, and workforce coordination that were far more advanced than traditional historical accounts have recognized. These administrative achievements were every bit as impressive as the engineering and construction achievements they supported. The mystery of pyramid construction dissolves when we examine the organizational evidence with proper appreciation for ancient administrative capabilities. These projects weren't managed by primitive people struggling with simple coordination challenges through informal leadership structures. They were directed by accomplished administrators who developed systematic approaches to project management that enabled unprecedented achievements through sophisticated organization of human effort and resources. The legacy of pyramid construction organizational systems continues to provide insights and inspiration for modern project management and administrative challenges. The principles of coordination, quality control, and resource management demonstrated in pyramid construction remain relevant to contemporary industrial and construction operations that face similar challenges of scale, complexity, and precision. The human achievement represented by pyramid construction organizational systems deserves recognition alongside the engineering and construction achievements as evidence of sophisticated capabilities that enabled ancient civilizations to accomplish objectives that continue to challenge modern understanding of what human organizations can achieve when they operate at the highest levels of administrative competence and coordination. The preservation systems that protected pyramid construction materials and completed work from environmental damage reveal another dimension of ancient Egyptian sophistication that goes far beyond simple building techniques. The desert environment presented constant threats to both ongoing construction and finished surfaces, requiring protective measures that demonstrate advanced understanding of materials, science, and environmental engineering. Sand infiltration posed one of the most persistent challenges to pyramid construction quality. The constant wind-blown sand could damage precision-cut surfaces, interfere with the fitting of blocks, and compromise the smooth finishes that were essential to the pyramid's final appearance. The ancient Egyptians developed covering systems and protective barriers that shielded work areas during construction, while allowing continued access for workers and materials. These protective systems weren't simple tarps thrown over work areas. They were engineered structures that could withstand desert windstorms while maintaining the controlled environment necessary for precision construction work. Archaeological evidence suggests sophisticated temporary roofing systems and windbreak walls that created protected workspaces within the broader construction site. The preservation of cutting tool effectiveness in the abrasive desert environment required maintenance procedures that kept copper chisels and bronze saws functioning despite constant exposure to sand and dust. The ancient Egyptians developed cleaning and resharpening techniques that maintained tool performance throughout extended construction periods, along with storage systems that protected tools from corrosion and damage when they weren't in active use. Water management during construction presented challenges that extended beyond the hydrostatic leveling systems we discussed earlier. The enormous workforce required reliable supplies of fresh water for drinking, cooking, and construction activities, while wastewater had to be managed to prevent contamination and maintain sanitary conditions throughout the worker settlements. The ancient Egyptians engineered water distribution systems that delivered fresh water from the Nile to construction sites and worker villages through networks of channels and storage facilities. These weren't simple ditches carrying river water. They were designed distribution systems that maintained water quality while providing adequate supplies for populations that could reach 30,000 people during peak construction seasons. Waste management systems handled the enormous quantities of organic waste generated by large construction workforces while preventing contamination that could cause disease outbreaks. Archaeological evidence shows organized disposal systems and sanitation facilities that maintained health standards throughout worker settlements that house populations equivalent to major cities. The preservation of completed construction work required protective measures that prevented damage from ongoing construction activities while allowing continued access for additional work. Lower courses of pyramid masonry had to be protected from damage caused by the movement of heavy blocks for upper courses, while finished surfaces had to be preserved until final completion and cleaning of the entire structure. Material storage systems protected stone blocks, tools, and other construction materials from damage while maintaining organized inventories that enabled efficient retrieval when items were needed. These storage systems had to accommodate materials with widely varying characteristics, from delicate finished casing stones that required careful handling to massive granite blocks that demanded heavy-duty storage infrastructure. The quality preservation procedures that maintained construction standards throughout extended construction periods involved systematic inspection and maintenance of completed work to ensure that precision achieved in early construction phases would be maintained throughout the project. Settlement, weathering, and construction activities could all affect previously completed work, requiring ongoing monitoring and corrective action. Climate control measures protected both workers and construction materials from the extreme temperature variations that characterize desert environments. Daytime temperatures that could exceed 100 degrees Fahrenheit created dangerous working conditions and could damage certain construction materials, while nighttime temperatures that dropped dramatically created thermal stress that could crack stone surfaces or damage tool performance. The ancient Egyptians developed work scheduling systems that coordinated construction activities with environmental conditions to minimize weather-related problems while maintaining construction progress. Peak construction work was scheduled during cooler parts of the day, while more demanding activities were planned around seasonal weather patterns that affected working conditions and material performance. Structural monitoring systems tracked the behavior of completed construction work under the loads imposed by ongoing construction activities. As pyramid construction progressed, an additional weight was added to lower courses. The ancient builders had to verify that previously completed work continued to perform correctly and that no structural problems were developing that could compromise the integrity of the entire structure. The development of these sophisticated preservation and protection systems required engineering knowledge that anticipated problems and developed solutions before those problems could affect construction quality or worker safety. The ancient Egyptians couldn't simply react to problems as they occurred. They had to plan protective measures that would prevent problems from developing in the first place. Material compatibility studies ensured that different construction materials would work together effectively over extended periods, without creating chemical reactions or physical incompatibilities that could compromise structural performance. The combination of limestone, granite, and various metals in pyramid construction required understanding of how these materials would interact under load and environmental exposure across centuries of service. Environmental testing procedures verified that construction materials and techniques would perform adequately under the specific environmental conditions present at construction sites. The ancient Egyptians developed testing methods that could predict long-term performance based on shorter-term observations, enabling them to select materials and techniques that would provide adequate durability for monuments intended to last forever. The integration of preservation systems with construction procedures demonstrates planning capabilities that considered not just immediate construction requirements, but also long-term maintenance and protection needs. Every construction decision had to account for its effects on the preservation and protection of both ongoing work and completed elements. Documentation systems recorded preservation procedures and protection measures so that successful techniques could be replicated in future projects and modified approaches could be evaluated for effectiveness. The ancient Egyptians maintained records of what preservation methods worked well and what approaches proved inadequate, building institutional knowledge that improved with each construction project. Training programs ensured that workers understood preservation requirements and protection procedures that were essential to maintaining construction quality. Workers had to learn not just how to perform their primary construction tasks, but also how to work in ways that protected completed work and maintained the controlled environments necessary for precision construction. Emergency response procedures planned for environmental events and construction accidents that could threaten completed work or endanger construction personnel. Desert sandstorms, flash floods, and construction accidents all required prepared responses that could minimize damage and maintain construction progress despite unexpected challenges. The success of these preservation and protection systems becomes evident in the condition of pyramid construction that has survived to the present day. The precision and quality of ancient work remains apparent in measurements taken with modern instruments, demonstrating that preservation procedures successfully maintained construction standards throughout extended construction periods and across thousands of years of environmental exposure. Innovation in preservation techniques continued throughout pyramid construction periods as builders learned from experience and developed improved methods for protecting materials and completed work. The ancient Egyptians didn't simply apply inherited preservation knowledge without modification. They actively developed new approaches and refined existing techniques to meet the unprecedented challenges of pyramid construction. The economic impact of preservation and protection systems represented significant investments in infrastructure and procedures that were essential to successful project completion. While these systems didn't contribute directly to construction progress, they were necessary to maintain the quality and integrity that made construction progress meaningful and sustainable. The technological sophistication of preservation systems challenges assumptions about ancient capabilities and demonstrates engineering knowledge that was far more advanced than traditional historical accounts have recognized. The ancient Egyptians developed systematic approaches to materials protection and environmental control that incorporated principles of chemistry, physics, and engineering that wouldn't be formally described until modern times. The organizational requirements for implementing comprehensive preservation and protection systems across massive construction projects demonstrate administrative capabilities that coordinated multiple specialized activities while maintaining focus on primary construction objectives. The successful integration of preservation requirements with construction procedures required management skills that balanced competing priorities while achieving overall project goals. The legacy of ancient preservation and protection techniques continues to inform modern approaches to construction quality control and environmental protection during large-scale building projects. Contemporary construction managers study ancient methods for insights that can enhance modern preservation procedures and protection systems. The evidence for sophisticated preservation and protection systems provides additional confirmation that pyramid construction was achieved through advanced engineering and organizational capabilities rather than primitive methods or external intervention. The systematic approaches to materials protection and environmental control demonstrate planning and implementation abilities that were far more sophisticated than traditional historical accounts have suggested. As we examine the final elements that completed these magnificent structures, we encounter engineering challenges that pushed ancient capabilities to their absolute limits, while maintaining the mathematical precision and structural integrity that have allowed these monuments to endure for over 4,000 years. The capstone installation and final surface preparation required techniques that coordinated multiple complex operations while achieving perfection that remains visible today. The pyramidion, or capstone, that crowned each pyramid presented installation challenges that required lifting techniques capable of positioning substantial weight at heights approaching 500 feet above ground level. These weren't small decorative elements that could be easily maneuvered. They were substantial stone blocks, often made from granite or other hard materials, that had to be shaped to precise specifications and positioned with extraordinary accuracy to complete the geometric perfection of the entire structure. The lifting systems required to install pyramidions at such heights demonstrate mechanical engineering capabilities that multiplied human force through sophisticated applications of leverage, counterweights, and coordinated team effort. The ancient Egyptians had to develop techniques that could handle substantial loads at extreme heights while maintaining the precision necessary for perfect positioning of the final structural element. The surveying accuracy required to ensure that pyramidions would complete the intended geometric relationships of the pyramid structure demanded measurement techniques that could verify alignment and positioning across hundreds of feet of vertical distance. Any error in pyramidion placement would be visible as an imperfection in the pyramid's profile when viewed from ground level, compromising the visual impact of the entire monument. The final surface preparation that created the smooth, polished exterior finish of completed pyramids required systematic approaches to surface grinding and polishing that achieved consistency across millions of square feet of stone surface. This wasn't casual finishing work that could be completed with simple hand tools. It required organized procedures that maintained uniform surface quality while coordinating the work of numerous craftsmen across the entire exterior of the structure. The precision of this final finishing work becomes apparent when you examine the few remaining original casing stones that still survive on the Great Pyramid. The surfaces are polished to smoothness that approaches optical flatness, with tool marks so fine that they're barely detectable even under magnification. The joints between adjacent stones are so precise that detecting the boundaries between individual blocks requires careful examination. This level of surface quality required finishing techniques that controlled every aspect of grinding, polishing, and final preparation. The consistency of results across thousands of individual blocks demonstrates manufacturing capabilities and quality control procedures that maintain standards throughout the entire finishing process. The coordination required to complete final finishing work without damaging previously completed construction, presented logistical challenges that required careful planning and systematic execution. Workers had to access all exterior surfaces of the completed pyramid while avoiding damage to precision finishes and maintaining the structural integrity of scaffolding and access systems at considerable heights. The tool requirements for final finishing work included specialized grinding and polishing implements that could achieve the required surface quality while remaining manageable for workers operating at extreme heights. The ancient Egyptians developed finishing tools that were effective, durable, and safe for use under challenging working conditions. The quality control procedures that verified final finishing work had to ensure that every surface met specifications before the project could be considered complete. These inspections had to detect and correct surface imperfections that could compromise the visual impact of the completed monument while maintaining overall project schedules and worker safety. The completion ceremonies that mark the successful conclusion of pyramid construction demonstrate the cultural and religious significance these projects held within ancient Egyptian society. The monuments weren't just impressive engineering achievements. They were sacred structures that fulfilled specific religious and cultural functions that gave meaning and importance to the enormous efforts required for their completion. The preservation measures implemented to protect completed pyramids from environmental damage and human interference reveal long-term planning that anticipated maintenance requirements and protection needs across centuries of exposure to weather, earthquakes, and human activities. The ancient Egyptians designed these monuments to last forever, and they included systems that would help ensure their preservation for future generations. The documentation systems that recorded construction methods, organizational procedures, and lessons learned from pyramid construction created institutional knowledge that influenced Egyptian engineering and construction for centuries afterward. The techniques and organizational methods developed for pyramid construction found applications in temples, palaces, and other monumental projects throughout Egyptian civilization. The training programs that preserved construction knowledge and transmitted it to future generations of craftsmen and engineers ensured that the capabilities developed through pyramid construction wouldn't be lost when individual master builders retired or died. These educational systems maintained institutional competence across generations of construction projects. The economic systems that supported pyramid construction created infrastructure and organizational capabilities that contributed to Egypt's prosperity and political influence throughout the ancient world. The concentration of skilled craftsmen, advanced tools, and sophisticated organizational systems created competitive advantages that extended far beyond monumental construction projects. The technological innovations developed for pyramid construction influenced engineering and construction practices throughout the ancient Mediterranean world through trade relationships and cultural exchange. The legacy of pyramid construction techniques can be traced through architectural developments in multiple ancient civilizations across centuries of history. The scientific principles demonstrated in pyramid construction provided foundations for mathematical and engineering knowledge that influenced intellectual development throughout ancient civilization. The integration of theoretical knowledge with practical application created understanding that advanced human knowledge of geometry, physics, and engineering across multiple disciplines. The organizational achievements represented by successful pyramid construction demonstrate administrative and management capabilities that enabled ancient civilizations to coordinate human effort on scales that wouldn't be matched again until the modern industrial era. These administrative innovations influenced governmental and commercial organizations throughout ancient history. The cultural impact of pyramid construction extended throughout ancient society and influenced art, literature, religion, and social organization in ways that shaped Egyptian civilization for millennia. The monuments served as symbols of human achievement that inspired generations of people to pursue ambitious objectives through organized effort and sophisticated planning. The international influence of pyramid construction attracted visitors, scholars, and craftsmen from throughout the ancient world who came to study Egyptian techniques and adapt them for use in their own construction projects. The pyramids became centers of technological and cultural exchange that influenced development throughout the ancient Mediterranean region. The preservation of these monuments across more than 4,000 years provides ongoing testimony to the sophistication of ancient construction methods and the effectiveness of preservation measures implemented by their builders. The continued existence of the pyramids demonstrates that ancient engineering and construction capabilities were far more advanced than traditional historical accounts have recognized. The modern relevance of pyramid construction achievements becomes apparent when contemporary engineers and project managers study ancient methods for insights that can inform current, large-scale construction projects. The principles of precision construction, quality control, project coordination, and organizational management demonstrated in pyramid construction remain applicable to modern industrial challenges. The evidence overwhelmingly demonstrates that pyramid construction was achieved through sophisticated engineering, advanced organizational systems, and systematic application of scientific principles by highly capable ancient civilizations. No extraterrestrial intervention was required because human beings, when working at their intellectual and organizational peak, are capable of achievements that continue to inspire awe and admiration thousands of years after their completion. The ancient Egyptians who built the pyramids deserve recognition as accomplished engineers, skilled craftsmen, and organizational masters who developed revolutionary solutions to unprecedented challenges through human ingenuity, applied with extraordinary focus and determination. Their achievements represent the pinnacle of ancient human capability and provide permanent testimony to what people can accomplish when they dedicate themselves to pursuing seemingly impossible objectives through sophisticated planning and coordinated effort. The mystery of pyramid construction dissolves when examined with proper appreciation for ancient Egyptian capabilities and achievements. These monuments weren't built by primitive people with alien assistance. They were created by intellectually sophisticated civilizations who developed advanced engineering and organizational techniques that enabled unprecedented construction achievements through systematic application of human knowledge and capability. The legacy of pyramid construction continues to inspire modern engineering and organizational achievement while providing evidence that challenges assumptions about technological progress and human capability throughout history. The pyramids stand as permanent monuments to human achievement that demonstrate what becomes possible when intelligence, determination, and resources are coordinated effectively toward ambitious objectives that push the boundaries of what seems achievable within the constraints of available technology and knowledge. The broader implications of pyramid construction extend far beyond the monuments themselves, revealing technological and organizational innovations that fundamentally transformed ancient civilization. When we examine the ripple effects of these massive projects, we discover that pyramid building didn't just create impressive tombs. It catalyzed developments in engineering, administration, and scientific understanding that influenced human progress for millennia. The metallurgical advances developed specifically for pyramid construction revolutionized toolmaking throughout the ancient world. The copper alloys perfected for cutting limestone and granite weren't just useful for monument building. These same alloys found applications in agriculture, warfare, and manufacturing that enhanced productivity across Egyptian society. The techniques for work-hardening metals, developed to maintain sharp cutting edges on construction tools, improved everything from farming implements to weapons to household items. The mathematical knowledge embedded in pyramid construction established Egypt as the ancient world's center of geometric and engineering expertise. The precise calculations required for maintaining geometric accuracy across structures spanning hundreds of feet created mathematical techniques that were applied to everything from land surveying after Nile floods to architectural planning for temples and palaces. The understanding of proportional relationships and angular measurements developed for pyramid construction became standard knowledge that influenced design principles throughout Egyptian civilization. The transportation innovations created for moving massive stone blocks transformed commerce and trade throughout the ancient Mediterranean. The specialized barges designed to carry 70-ton granite blocks down the Nile became prototypes for cargo vessels that revolutionized river and maritime transportation. The road engineering techniques developed to handle extreme loads created transportation infrastructure that facilitated trade and military movements for centuries afterward. The organizational systems pioneered for coordinating tens of thousands of workers became templates for governmental administration that enhanced Egypt's political and military effectiveness. The record-keeping systems, communication procedures, and hierarchical management structures developed for pyramid construction were adapted for tax collection, military organization, and large-scale agricultural projects that strengthened Egyptian power throughout the ancient world. The quality control procedures established for maintaining construction precision created standards of excellence that influenced Egyptian craftsmanship across multiple industries. The systematic inspection methods, measurement techniques, and approval processes developed for pyramid construction were applied to pottery production, textile manufacturing, metalworking, and other crafts that enhanced Egypt's reputation for high-quality goods throughout ancient trade networks. The seasonal workforce management systems, created for accommodating flood season laborers, established patterns of employment and economic activity that provided stability and opportunity for Egyptian workers long after pyramid construction ended. The training programs, skill development procedures, and career advancement opportunities created for pyramid workers influenced labor practices throughout Egyptian society. The supply chain management innovations developed for coordinating materials from sources scattered across Egypt and beyond created commercial networks that enhanced trade relationships and economic prosperity throughout the region. The procurement procedures, inventory management systems, and logistics coordination developed for pyramid construction were adapted for other large-scale projects that continued to benefit Egyptian society for generations. The scientific instruments and measurement techniques developed for pyramid construction advanced Egyptian capabilities in astronomy, surveying, and navigation that enhanced everything from agricultural planning to maritime exploration. The precision measuring tools, alignment procedures, and calculation methods created for pyramid construction became standard equipment and knowledge that influenced scientific development throughout ancient civilization. The architectural innovations pioneered in pyramid construction influenced temple design, palace architecture, and urban planning throughout Egyptian history. The structural engineering principles, load distribution techniques, and foundation systems developed for pyramid construction were adapted and refined for other monumental projects that continue to demonstrate Egyptian engineering superiority for centuries. The preservation techniques developed for protecting pyramid construction materials and completed work created knowledge of materials, science, and environmental engineering that influenced construction practices throughout the ancient world. The understanding of stone properties, weathering resistance, and long-term durability developed through pyramid construction enhanced the quality and longevity of buildings throughout Egyptian civilization. The international influence of pyramid construction techniques spread through diplomatic contacts, trade relationships, and cultural exchange to influence engineering and construction practices throughout the ancient Mediterranean and beyond. Visitors from other civilizations studied Egyptian methods and adapted them for use in their own construction projects, spreading pyramid construction innovations across multiple cultures and regions. The educational systems established for training pyramid construction workers created institutional knowledge preservation that influenced Egyptian society's approach to skill development and knowledge transmission. The apprenticeship programs, master craftsman training, and technical education procedures developed for pyramid construction became models for professional development throughout Egyptian civilization. The economic impact of pyramid construction created prosperity and technological development that enhanced Egypt's competitive position throughout the ancient world. The concentration of skilled craftsmen, advanced tools, and sophisticated manufacturing capabilities created economic advantages that benefited Egyptian trade, agriculture, and military effectiveness long after pyramid construction was completed. The technological innovations developed for pyramid construction established Egypt as the ancient world's leader in engineering and construction technology. The reputation for technical excellence created through pyramid construction attracted students, craftsmen, and scholars from throughout the known world who came to learn Egyptian methods and adapt them for use in their own civilizations. The administrative innovations pioneered for pyramid construction influenced governmental organization and public works management throughout Egyptian history. The project management techniques, resource allocation procedures, and coordination systems developed for pyramid construction were adapted for other large-scale public projects, including irrigation systems, temple construction, and military campaigns that demonstrated Egyptian organizational superiority. The cultural significance of pyramid construction within Egyptian society created symbols of human achievement that inspired artistic, literary, and intellectual development for millennia. The monuments served as evidence of what human beings could accomplish through organized effort and sophisticated planning, encouraging ambitious undertakings throughout Egyptian civilization and beyond. The preservation of pyramid construction knowledge through institutional systems ensured that technological and organizational innovations would continue to benefit future generations, rather than being lost when individual master builders died or retired. The systematic documentation and knowledge transmission procedures developed for pyramid construction became models for preserving and advancing human knowledge across multiple disciplines. The pyramids stand today not as monuments to alien intervention, but as eternal testaments to human ingenuity operating at its absolute peak. When you look at these ancient wonders now, you're not seeing the impossible made manifest by extraterrestrial visitors. You're witnessing what happens when brilliant minds, skilled hands, and unwavering determination converge with unprecedented focus and resources. The ancient Egyptians didn't need visitors from the stars because they possessed something far more powerful: the limitless potential of human creativity and organization applied without compromise to achieve the seemingly impossible. These monuments will continue to inspire us for millennia to come, reminding us that the greatest mysteries of our past aren't solved by looking to the skies, but by recognizing the extraordinary capabilities that lie within ourselves.